This great iron bird was one of 6 dummies made to duplicate the weight distribution and moments of inertia of a combat-loaded F-100. Crude boxes hanging below the stubby wings represented the external stores, with the landing gear giving the only clue that this was a mock airplane. The dummy was one member of a 3-unit team, just a simple structural steel cross filled with concrete. The second unit of this team was staked out on the south lake bed at Edwards. This was our launcher, a multi-wheeled roadable trailer, which is a portable airstrip. It has a pair of ramps to support the wheels and a guide to control the flight path for the first 24 inches. This C-rail is our flight strip, designed to give directional and pitch guidance during takeoff. Then the third member of our team, the solid propellant booster. It will respond with a force of 130,000 pounds with a burning time of 4 seconds. Mechanically fitting the booster bottle to the aft section was a routine task. A more precise job is bore sighting. The center of thrust must pass through the dummy's center of gravity to give a flight path that is predictable. The line of flight, the trajectory, was planned to take the Iron Bird out half a mile with a peak altitude of 300 feet. When the dummy was raised to the 20-degree position, the crew retired to a safe distance, and we are ready for the first shot. Test engineers reviewing the results took a long, careful look at the high-speed films. They wanted to know why the dummy nosed up so sharply, what was giving us the high initial pitch rate. Careful analysis pointed up the C-rail, our takeoff runway, as an offender. It was forcing the tail down as it left the launcher. So the takeoff run was cut from 2 feet to 3/8 of an inch. And on run number 2, attention was concentrated on how the dummy round left the launching platform. The C-rail fix reduced nose-up pitch rate to a level predicted for this shot. On run 3, we checked the effect of a change in bore sighting. It gave us a longer trajectory, a flatter flight path. The fourth shot rechecked the launching techniques, and its success set the date for the first live flight. Our launcher was designed to be self-sufficient, to handle all the airplane's pre-flight service needs in a remote area away from normal power sources. The gasoline engine gives the power to winch the plane or the rocket booster up into position. It compresses air for engine starting, generates AC and DC power, pressurizes a hydraulic system that raised the plane and serviced its systems. We were set to shoot the plane out toward the open lake bed, putting a 7-mile landing strip ahead of the pilot should an emergency develop. Our project pilot assigned was Blackburn, a veteran of 6 years jet testing. He'd put in many hours in the flight simulator, made carrier-type catapult shots, rode the centrifuge to get the feel for the forces of this flight.
Booster temps within 2 degrees and ambience right on, Blackie.
Well, about that time, Frank. Let's get on with it.
Don't miss the fire signal. We'll run out of film. Blackie, have a good trip.
Okay.
combat load for this flight is a T-63 store and a 275-gallon tank, bringing weight up to 34,400 pounds.
Looks okay, Blackie. Can't see any marks on the fuselage. How'd it go?
Piece of cake, Bob. Piece of cake.
Two weeks later, the airplane was ready for launch number 2. All conditions were the same. Weight, bore sight, stores, all identical with the first flight.
Blackie, that booster case is still hanging on.
It may fall off any minute. I'm going to get some altitude and head out over the bombing range.
The mechanism of booster ejection, which had worked dozens of times in static tests, had functioned perfectly 5 times in actual flight, now stubbornly refused to release the booster case. During the next hour and a half of flight, the pilot tried every technique. Positive G, negative G, snaking, rolling, but the booster case still clung to the fuselage. But even this crisis developed one positive fact: the airplane can be flown in this condition.
Okay. Okay, we'll tell him. Blackie,
Yeah, Frank.
we've kicked it around and decided that a landing is just too hazardous. The booster case hangs below the gear. You better get out while you still have fuel.
Okay, I've got a chase plane with me. How about getting a helicopter out here so I don't have to walk home?
It's on its way.
Examination of the jettison mechanism showed that shear bolts, designed to fail under the force of booster thrust, did not part. These bolts were laboratory tested and found identical to previous ones used. We later found that the mechanism locked and blocked the necessary shearing action. The next dozen weeks were spent in instrumenting another ZELL airplane and making another dummy shot with a redesigned jettison system. The new system has explosive bolts, giving the pilot an option of booster case jettison any time after burnout if the case fails to drop normally. By the 3rd week in July, piloted shot number 3 was ready. Launch conditions and launch procedure were the same as on earlier shots. It appeared that our booster drop-off problem was solved, so we went on to make a series of 5 additional shots in July, checking repeatability. Flights were made on a 1-a-week basis with uniform, predictable results and no emergencies. Up to now, this has been Blackburn's one-man show, but on Flight 8, Captain Titus, the Air Force project pilot, stepped in to try his hand at a ZELL launch. Now we're just about to see if a launch is affected by individual pilot technique. landing, Captain Titus said,
No problem. I think any pilot qualified in the F-100 could handle the launch.
5 days later, he was back to repeat his performance, and the launch went off without incident. We continued our engineering evaluation on Launch 11. With bore sighting the only sensitive element, we wanted to find the maximum error tolerable. Nose up and nose down errors were purposely built in. We also cut the tie downs on the launcher, left it held only by its wheel brakes. No change in its efficiency was noticed. It performed equally well either way. Then we turned to increasing the airplane's weight with more fuel tanks and consequently more tactical range. Adding two 200-gallon tanks at inboard stations ups the combat radius by 190 miles, with the plane tipping the scales at 37,500 pounds. A total of 3 shots were made on the long-range version. Then the annual Air Force weapons meet at Nellis Air Force Base gave us the chance to show the ZELL launch system in an operational environment. We're simulating a tactical deployment of the launcher, a demonstration of its mobility. Under service conditions, the launcher would be towed to an airstrip close to a sensitive tactical area. In our trip to Las Vegas, we used a 200-horsepower diesel tractor and held open road speeds up to 45 miles an hour. We covered the 250 miles in 10 hours and were able to stay with other commercial vehicles threading our way through town. At Indian Springs, we met the ZELL airplane and loaded it for its 16th shot. Its gaudy test colors had been replaced by sober Air Force markings. A 275-gallon tank took the place of the T-63 store for this first public view of a ZELL launch. Moving out to our firing site illustrated another phase of deployment. The airplane launcher combination is towed over roads that degenerate from paved to gravel to tracks in the desert. Supporting its load over 14 wheels, our mobile airstrip was able to move out over the sandy desert floor without any tendency to bog down. Our remote site was reached in the afternoon, and the crew turned to preparing Air Force 947 for ZELL flight number 16. Since its first shot in July, launches were made on an average of 1 every 4 days, with no special maintenance problems arising. This is the culmination of Project ZELL, an F-100 spotted in a remote non-target area, ready, waiting for a quick launch into flight, ready but not impatient, since it can stay poised and set to strike for as long as 60 days. All we need to add is a pilot, who can be anyone qualified in F-100s, and a small crew. Under a real alert, with scramble conditions, time to launch would be about 5 minutes. Just the time necessary to start and check the engine, raise the airplane, make a last check in afterburner. We're in our operational area now. No instrumentation, no elaborate timing. Just a simple visual signal, and the 100 roars into flight.